This exercise considers the development of a delta. The aim is to explore in a 2D Delft 3D model the morphodynamic development of a delta. And we're going to set up a 2D Delft 3D model. We are going to enjoy the delta formation in some nice movies. We're going to play with some relevant parameters. These are three examples of world-famous deltas. The Mahakam Delta, the Walker Delta, and the Mississippi Delta. And they both have all three are conditions where considerable river flow and sediment supply by a river flow into the ocean or a lake where the sediment deposits and where the delta can prograde. And the wave action, for example, these deltas will be smoothed out along the shoreline, and tidal motion can also significantly reshape the delta here. We are not considering tides and waves. We're going to make a very simplified condition here. This also mimics basically reservoir infilling. If you have a river and you construct a dam blocking the river flow, you create an artificial lake. And where the river enters that artificial lake, it deposits also its sediment, and where an underwater delta then will develop as well. So you may also consider this an exercise in reservoir infilling. We are going again to approach the problem very schematically and simply. In a rectangular grid of 5 by 5 kilometers with a grid size of 50 by 50 meters. One of the boundaries is the river supply boundary, and the other boundaries we keep the water level at zero, a constant water level. So that means that water can flow out through any of the three boundaries, but the sediment will remain in the basin. A sand of 200 micrometers, bed slope factor alpha BN of 50, and a time step of 1 minute, and initially linearly sloping bed level from -10 to -1 meter. I created this working directory called Delta Development, where I will start my Delft 3D exercise by creating the grid in RGF Grid. Under operations, I can create my rectangular grid with grid cells of 50 by 50 meters, and the amount of cells is the number of cells is 100 by 100, and my grid size is 550 by 50 meters. Saving the grid, exporting it, grid. I call it 001. Close RGF Grid and opening QuickPlot or Quicken to import the grid here and to put the depth in. Now we have to impose a linearly sloping bed. And we do that as follows. We can define a depth value at any of these points. Here the depth is 10 meters. Mind you, it's positive, it's a depth value. It's not a bed level value. A bed level value would be negative compared to a reference level of 0. The water depth here is 1. Now you do not see anything appearing here, and that is because of the view settings. If we go on the view and we go to depth, it's now in continuous shades, but we can also put it to colored dots. And here you can see indeed that we have a depth of 10, and here at this point a depth of 1. We're going to interpolate between these 2 points by by edit, depth linear. Clicking first the left point of 10 meters and then the right point with the left mouse button. Quicken automatically interpolates the depth on in the underlying grid cells. Another operation will fill the remainder of the grid by a line sweep algorithm. Again, clicking the two endpoints of the line will create this nice linearly sloping bed level. I'm going to save the depth file, export depth, call it 001 as well. So now we created the grid and the depth. We are going to fill the model under flow input. In the domain, we open the grid 001, the enclosure file, don't forget that. The bathymetry, open. And we're going to the next step, the time frame. Again, we take 1 month. And the process is we have to add sediment here. We call that sediment send. And the initial conditions are a water level of 0, which is okay, and no sediment concentration, that's also okay. The boundaries, it's important. View the visualization area. I'm going to add the river boundary. The river boundary should have a width of 500 meters with a grid cell of 50 meters. That means that we need to have 10 cells. I'm going to zoom in my box here. I'm going to select 10 cells. Not necessary that it is exactly in the middle. Add the boundary. Zoom reset. And this is then the river boundary. We put in their current of 1 meter per second by a time series. And what I'm now doing is wrong. I will explain you why. You see in the visualization area that the M direction is positive to the right. That means the M value here is low, and the M value here of the coordinate system is high, so it goes from left to right. The river inflow goes from right to left, and that means that it is against the M direction, so we have to define that in a negative way, -1. If we would define positive values here, the boundary condition would suck out the water. So I rename the boundary here to a boundary called river. It's a time series. The Thatcher-Harleman time lag is not important here because we don't have tidal conditions. And the transport conditions, defining them is also not necessary because later on we will define equilibrium sediment concentrations here. And that will override the transport conditions defined over here. What I still have to do is to define the other 3 boundaries. And the upper part, the west part, and the south part. And I'm going to rename them indeed as being north, west, and south. Now on the northern side, the water level will again be time series. Added flow conditions, I'll put them at 0. So the water level, I just assume the water level will not change. which may be true for an ocean without tides or a very big lake. That means that although there is supply of the river, water supply of the river, it doesn't impact on the boundary conditions, on the overall amount of water in the lake. Okay, it's always good to save these boundary definition separately. Now, important aspect here. We are running for 1 month, and maybe later on we decide to run for 2 months. The time frame we can then say, yeah, 1 month is too. Let's run for not 1 month but for 2 months. The model will give an error, and the error will be related to the fact that your boundaries are still defined with respect to 1 month. So your model reads it needs to run for 2 months, but the boundaries are only defined for 1 month. Gives a lot of error. So a workaround here could be not to define it in terms of time series, but to define it in terms of a harmonic condition. Harmonic condition is a sine function, and the sine function has a frequency here is 30, so it means 12 hours. It's basically a tidal, semi-diurnal tidal cycle. You can define the amplitudes here, but if you put the amplitudes here to 0, that means that there is no tidal signal at all. And we close it. It's always valid whether you now run for 1 month or for 10 years. It always will apply that harmonic signal. So that's also what I'm going to do here. Make it harmonic, put everywhere 0 here. No tidal signal, only a constant value. We can also do that for the river flow. We can also make that harmonic, and we have to make it then not 0. No. We have to make that -1. Tricky thing. Yeah. So this is boundary conditions. I'm going to save it again. 001. Yes, close. Physical parameters. Just apply the roughness CSE value, viscosity, and we'll keep that as it is. A sediment, I'm going to use 200 mu with a sediment thickness of 5 meters. That's also okay. And the morphology, I update the bathymetry during flow simulation. That's true. I have my equilibrium sand concentration profile at the inflow boundary, so it overrides the boundary defined values. And my morphological scale factor is 100. Also, I use a spin-up interval before morphological change start, and I am ready to go here. Numerical parameters. Don't touch it. No operations. Monitoring. It's always compulsory to add 2 observation points. I'll make it 3. Maybe it's also nice to add a cross section or 2. Maybe I can make the cross section along the boundary here and at the boundary here. Cross sections are not compulsory. So this one is sea boundary, and this is called river boundary. No additional parameters. The output is automatically changed to 2 months. You see that also here. I put my output interval at 60 for the map file and the history interval for the observation points and the cross sections at 10 minutes. Now save all. The set file, the more file, the MDF file. Everything is saved. Now I know I made a mistake in this model, and it's supposed not to run. So let's see what's happening here. I select my model to run 001. And probably will give an error. Yes. So if you see this, you could panic and you could grab the phone and try to call me or email me. But the alternative is to open the diag file. So the diag file, it's called td-diag point.001. So it belongs to the 001 MDF file. And this file is always created. It's basically what the software gives back to you. It reports what it is doing. And the error here, what it states is that the last time in file 001.bcc for section river is smaller than simulation stop time. What does it mean? The BCC file defines the sediment concentrations at the boundary. So although we are overriding it because we define equilibrium sediment concentrations, it's still there. And apparently the time defined in the BCC file is not right. It's smaller than the simulation stop time. So if we go there, under boundaries, and the BCC file is the transport, is where the sediment concentrations, the concentrations of the constituents are defined. You can still see here that it is at the old time definition. So we used to run for 1 month, but now we shifted to 2 months. But under the BCC file, the old time definition is still applied. So we have to change that. And unfortunately, under the BCC, under the transport conditions, we cannot apply this harmonic value. We have to do it for all the conditions here, all the boundaries. So I made this error on purpose to show, because this is an error that often occurs, and so we have to save all again. So you definitely are not the first one that will face this error. But I also made it on purpose so that you know when the model is blocking and when it is not running, you know what to do, and you may find some indications of what you did wrong in the diag file that you can just open in a text editor. So I hope and trust that the model is now running. I'll go back, start. Yes. So this model runs for 1 hour, 1.5 hours actually. Yeah, it's quite big. 10,000 cells, 1 minute, 2 months. It requires some time to run it, but we can already have a look in QuickPlot. Let's always do that. Nice to do that so that you know that the model is not leading to some strange results. Opening the trim file here. And I'm going to look at the erosion and sedimentation patterns. So 2 time steps of 1 hour, that means we are 10 hours already on our way. And that is past the morphodynamic spin-up, because the morphodynamic spin-up is 720 minutes, so that's 12 hours. So we need 12 time steps. We're now at 15 time steps, and that is past the morphodynamic spin-up time. So we should be able to see some delta development over here. Yeah. So we see indeed the supply of sediment by the river and the deposition of sediment by the river. There is still one thing that I forgot, so I'm going to close this animation or this run. And I forgot that in the more file we had to change the bed slope factor, so the downhill sediment transport. And because we are dealing with Van Rijn, the bed slope factor should be set at 50. We cannot do that in the conventional GUI, but we have to edit it by hand in the more file. And it's now set at 1.5. The alpha bin is 1.5. We should set it at 50 to see some more realistic patterns. Running it again. And I will stop my recording now. I'll be back to you in a few minutes when the run is finished. So I'm back. It has run for 7.5%. I opened the file in QuickPlot, at least the erosion sedimentation patterns, and I'm going to view that with symmetric limits. Yeah. And here you can see a beautiful delta developing. I'm going to make it even more beautiful by not plotting the erosion sedimentation patterns, but the bed level and water level points. I use a different color map. Call it Earth 1, or maybe no, Earth 2 is nicer. Quick view, and just not applying symmetric limits here. You can see here a nice delta developing in this animation. So the first 12 hours nothing happens. It's the morphodynamic spin-up or the hydrodynamic spin-up. And then we supply sediment. And you can see very nicely that there's shortcuts coming, there's an avulsion coming. And sometimes it builds out then, but then that means if the delta builds out, then the water level gradient can be shorter, and there's side channels, avulsions developing over there. It is spreading, it's supplying sediment. It's a little bit asymmetric. That may be due to the numerical scheme, but probably more. It is probably more clear that the boundary condition of the river is not exactly in the middle. So that gives on the right hand side and the left hand side slightly different bed level or water level gradients. I'm going to stop the animation here, and you should enjoy that as well. Well, this will continue forever, and it will in the end fill the entire basin. You can play with parameter settings like the morphological factor, the bed slope effect, alpha bn in the more file, and look at the differences that develop because of that. So thank you for your attention, and see you next time.